This video will be about exponential growth and decay. So when you're working with exponential growth or decay, this is the main equation. Y equals A times B to the x. A always stands for the principal or the initial amount. B will always represent the growth factor. This may be the exponential growth or the exponential decay factor. It can be both growth or the decay factor. And that growth factor does not include the x. The x is the variable. So these are often used for interest problems. So when we're working with interest, we have the principal or the starting amount. So let's say we have $4,000 in principal, and we're going to invest it in an account that earns 6% interest. And this will be compounded annually. So when you have something like this, we've got to figure out what numbers to put where. So our equation was y equals A times b to the x. A is always our principal or initial amount. So the principal given is $4,000. So instead of writing the letter A here, we'd write 4,000. B is the growth rate. Now this one, we've got to do a little bit of changing here. So it says 6% interest. That is how much we're growing by. But we already have an initial amount. We have 4,000. We're going to consider that 100%. So we want 100%, and then on top of that, we want the extra 6%. So really, we're going to be doing 106%. But when we plug this into a formula, we don't like it as a percentage. Percentages are always out of 100. So if we divide 106% by 100, we're not going to have this percentage symbol anymore, and we would get 1.06. So that's what would go into our equation. So we had A equals 4,000. We're going to have B is 1.06 to the x. Now x would be our time if we want to find out how much money we're going to have a couple years down the road. So let's say we want to find this after 5 years. Since we're compounded annually, we're not going to have to do anything else with our percentage, our interest rate. We're not going to have to do anything with our time. You'll see an example where if we're compounded quarterly or semi-annually or monthly, how it's going to change things. But if we're compounded annually, we get to just plug in 5 for x, and then plugging that into our calculator gives us $5,352.90. So if you've found somewhere to invest your money at a 6% interest rate, that's how much money you'd have after 5 years. So let's do an example where we have to be compounding quarterly. So quarterly means 4 times a year. If it said semi-annually, it'd be twice a year, and if it said monthly, it'd be 12 times a year. That's going to change our interest rate, and it will change our value we put in for the time. So our x variable. but it still won't change our initial amount. Our initial amount will still be $3,000. Because this one said we start with $3,000. Our interest rate is currently 4.5%. But if we're compounded quarterly, we're going to take that 4.5% and divide by 4. That gives us 1.125%. Now again, we have $3,000. We're considering that 100% of our money, and we want to earn 1.125 on top of that. So 100 plus 1.125 is 101.25%, which then we don't want it written as a percent, so we have to divide by 100. So that gives us 1.0125. That will be our growth factor. Next comes our time. If they don't give us a time, we just put X. Once they want a time, let's say after 7 years. Again, this is compounded more than annually. We're not just compounding once a year, we're compounding 4 times a year. So the first year we compound 4 times. The second year we compound 8 times total. 4 from the first year, 4 from the second year, so 8 total. Third year would be 12 total. So we have to do 7 times 4 to figure out what we put in for time. And that's because we were compounding quarterly. If it was semi-annually, we'd times by 2, or up here with our rate, we'd divide by 2. If it was monthly, we'd times by 12 because there's 12 months in a year, or divide by 12 on our rate because there's 12 months in a year. So now we have 3,000 times 1.0125 to the 28th. That gives us $4,247.98. So we have also exponential decay. When you have exponential decay, that growth factor will be a fraction smaller than 1. Or a decimal smaller than 1. So on this equation, 50 would be the initial amount. 0.7 would be the decay factor. Again, the decay factor does not include the x. So these can be used with half-life. So let's say we have the half-life of iodine 124 is 4 days. That means if you start with 200 grams or whatever of iodine 124, after 4 days you'd only have, it's decayed, it naturally goes away. So after 4 days you'd only have 60 grams, and 4 days after that, so after 8 days you'd have 30 grams. 4 days after that you'd have 15. So every 4 days you only have half of what you started with. A technician measures a 40 MCI sample of iodine 124. How many half-lives occur in 16 days? How much iodine 124 is in the sample after 16 days? So if our half-life is every 4 days, that means we have 1 half-life for the first 4 days. So if we do 4 more days after that, first 8 days, now we have another half-life, so 2 half-lives. Then if we did another 4 days after that, so 12 days, we'd add 1 more half-life, so 3 half-lives. So you can write it out like this if you want to follow the pattern, or you could just say, well, 16 days total divided by a half-life every 4 days is 4 half-lives. So then it says how much iodine 124 is in the sample after 16 days. So we're still using y equals a times b to the x. A is the initial amount, and we initially had a 40 MCI sample. So A would be 40. Now we're talking about a half-life, so we lose 50% every 4 days. 50% as a decimal. Again, we divide by 100%. That gives us 0.5. And then we would put the time, or how many half-lives have passed. So we don't use the 16, that's how many days have passed. We want to know how many half-lives have passed. So that's why we did this 16 divided by 4 up here. 4 half-lives have passed, so that's what we would put in for x. Plugging that into a calculator gives us 2.5. It is measured in MCIs. So that concludes our discussion on exponential growth and decay.